Good morning, everyone. Welcome to the workshop today. And in this workshop, we are going to go through a case study by rock weathering calculations. And we want to illustrate what data science is and just give you an intuitive understanding and provide some hands-on experience. So the motivation for this workshop is that as we as you may know, like data science relevant techniques has been transforming many research disciplines, including the geoscience. And what it is so someone may think it's a black box and some kind of scary. So here we want to go through the example and give some intuitive understanding and may help facilitate your future research. So this is I'm from this lab. Our lab is called Carbon Cycle and Earth Environment. So we focus on the carbon things. And I'm Shihan, and this is Cynthia. We both from the Department of Oceanography, and our research extensively uses the data science and modeling techniques. And let's start as all our materials are presented in compiled in are written in R codes and are compiled in Jupyter Notebook files. So the first step is to access and run the codes. So let's go to this data events website, which you can from your history or just search HPRC data science meets geoscience. You will go here and click the PDF here. We have materials here. So it's our walkthrough. It's with full tutorials on how to log in and how to download the files. The first one is go to the ACES portal. So you can go back to the event and click the portal here. Since I already log in, so I can come to the interface directly, and you may see some login requirements here, something like this. You just input your ID and password, then you can log in. So we will leave extra minutes after each section and for questions. So don't worry if you didn't follow up anything. Oh, good. Okay. So here's to login. After login, we go to click the files and go to the Scratch file. So I can just go there. This is my session. I go here, I click files and go to the Scratch one and open in terminal. You see the option here, open in terminal. And just we will enter an interface just like a terminal interface. Here and go back. Oh, is it to last? It's fine. It's okay here. And next step, just in the terminal, you can copy and paste the command here from CP and to the Scratch. And after this one, yeah, it's very fast, within 1 second. And go back to the dashboard and nothing happens here. So we refresh. You will see something new, a new folder here. It's called 2025, our carbon workshop. And we can open it. And you see the structure here is we will go through the 1, 2, 3 Jupyter Notebook files. And the image includes all the pictures incorporated in the Jupyter Notebook files and some data we will use. Installation is not irrelevant to the workshop here. It will tell you how to set up the environment and run the codes in your local laptop. So if you are interested, and you can follow the instructions here and go out, just play with the codes when you leave the workshop. And here's a structure for our data. So next one is how shall we run the codes? So still go back to the code here. We see something new in our folder. And next one, we will use the interactive sessions from the ASYS system. So still on the dashboard, we choose the interactive apps option here. And there is a Jupyter Lab GeoDS. We click this one. And everything has been set up by our coworkers, so you don't need to change anything. Just click the launch. And you should enter this interface. It's cute. So we just wait, click the connect to Jupyter Lab, and here we go. And now we can run our codes here. So we can start from the first one. Here's this one. And we will go one by one from the first one to the last one. And let's go, just turn on the first one. And if you run the codes one line by one line, and just you can click here, run the cell, and you can also use some shortcut, use the shift plus enter, and we just go one by one. So if anyone is here, so we can start the materials here. Yes, cool. That's great. So as mentioned earlier, in this workshop, we will explore a case study in rock weathering calculations. Then first thing first, why do we care about rock weathering? And there are multi aspects of the answer, but we start from the camera change, the most pressing one. So this figure, many of you might be very familiar with the figure shown here. For the left panel, axis is the time, and y-axis is a data temperature is a temperature change, and the y-axis, the red panel axis is still the time, and y-axis is the CO2 concentration. We see since 1850, the temperature has increased around 1.1 degrees, and correspondingly, the PCO2 also show a rapid rise. So this figure just shows us there's a close correlation between the PCO2 and global temperature. After that, you may have heard some words like reduction in carbon emission, but recent IPCC report has shown that just a reduction in CO2 emission cannot solve the climate problem, and we need to actively remove the carbon from the atmosphere. So this word is called carbon dioxide removal techniques. And here, this figure shows 10 options for negative emissions techniques, like including many like direct air capture. It just captures CO2 from the atmosphere and store the CO2 in somewhere. And also we see, you can have a close look later, but we see here one option called enhanced weathering. And previously it was called enhanced rock weathering. So now we see the enhanced the rock weathering here. Then comes the question, what is rock weathering? Where's the figure? Yeah. So here should be one image. Doesn't work? Okay. Yeah, we just go to the old one. I have an updated figure here, but something's wrong here. So you can just click the enter, and you enter your code should be river weathering.png, but we can change it to river weathering and just delete the two. So we can see what is rock weathering here. And here gives the example that silicate rock weathering. And in the silicate rock weathering, you can just see a chemical reaction from a silicate mineral and CO2, and it will generate some calcium ions and bicarbonate and silica. So you see the net effect. The CO2 is from the atmosphere, but after the reaction, the CO2 will move to the river. So in this way, the CO2 will be transferred from atmosphere and to the river. and the river will be transported to the ocean. In the ocean, the CO2, in the ocean, there will be the bicarbonate and the calcium, they will react and precipitate the carbonate rock here. So the net effect for silicate weathering is it can remove the carbon from the atmosphere and transfer into the sediments. So silicate rock weathering is a natural carbon sink in the natural world. That's the reason we focus on it. And next question is, how can we quantify the rock weathering flux? So from the equation here, we know that it will transfer from the bicarbonate. We can monitor the bicarbonate flux to reflect the CO2 removal flux. So for instance, we have a watershed and we just measure the water chemistry here. You see here the dot line is a river and here's the outlet. And we can measure the bicarbonate concentration in this region, in this outlet. And when we calculate the runoff. And then it's just a discharge per area. And finally, we can get something like flux is more per area and per time. So in this way, our calculation will be based on the riverine chemistry measurement. And to tackle the key questions, we need to know, we are very curious about two key questions. The first one is what factors control the rock weathering? The next one is how can we predict weathering flux in regions without river chemistry measurement? So that's basically and comes to two methodologies. The first one is physics-based simulation. So it's just like Newton's law and so many physics laws, and it's well established and we should be very familiar with. It begins with understanding of physical processes and follow some physical laws in rock weathering and use mathematical equations, sometimes very complicated mathematical equations to describe the processes and use some environmental variables to put into the model and it estimates the weathering flux. To give you just an intuitive understanding here, we have an example. For instance, we want to predict the rock erosion along a riverbank. Maybe sometimes the considerable factors will be water velocity. It's just the speed is higher, is more erosive, and a rock tap. And the rock tap sometimes is more erodible and less erodible, and water chemistry it's more erosive or less erosive. These factors, and we link these factors and its erosion along the riverbank with some mathematical equations. So, but for these questions, the challenge for the silicate weathering process is like in natural world, silicate weathering is very complicated. So that means some complex interactions between many variables is probably cannot be considered in the whole physical model. So that means the physical model is very difficult to incorporate all variables, and it will limit the accuracy and the scope of predictions. And alternatively, machine learning techniques offer some advantages over the traditional physics-based models. The biggest advantage is it can capture the intricate patterns and interactions among many variables. It can use many data to predict it, and we don't care about the physical processes inside and just use a statistical relationship between some environmental variables and our eventual output. That's a weathering flux. So it's especially useful when like in the silicate rock weathering, the relationships between the factors is not easily incorporated in a physical based model. So with this information in our workshop, we will begin by illustrating a classical physics-based model. And following this, we'll provide an example using machine learning to quantify the rock weathering flux. So with this, the key takeaways information will be included. First, you will have an intuitive understanding of and logic behind the machine learning techniques. And you will know the difference between the machine learning and the traditional method. And you will also gain some practical coding experience. So here's a workshop outline as we as we mentioned early, and it's again, if it's okay if you cannot follow, and we will leave extra minutes for questions, and you can also explore the codes by yourself. Some useful shortcuts here in the Jupyter lab. First one, for instance, I click E, and there will be a new cell above the current cell, and click B. Why it's so slow? Click B, and will be a new cell under. The next one, like D and D, you can try to play with it. Yeah, just delete, and I click Z. I just recover. And if you want to comment and uncomment some lines of code, you just use a command plus the slash or the control plus slash on your Windows laptop. But it's yeah. And last one is code. We use this, and we use art plus the minus and some shortcut here. And if you want to know more about it, you can search about it. You can also go back to the reference here. Firstly, we'll provide some basic introduction to data table and the spatial data set. Because we will manipulate the data here, but most basically use the data table, and it's a very powerful two-dimensional object. And we see here is the rows and columns, just something we see in the Excel. And we will use this one to explore the rock weathering relevant data. So first one, we create a new data frame, and use the str function can show the structure and the contents, and also some summary. It will give us a statistical summary, and we will use the data table library here. And it's a high performance, and also is a mostly commonly used in the geospatial data analysis. So just to emphasize that the idea here is you don't need to memorize all the function here, and we just want to give you a intuitive understanding like what data table can do here. And if you need some help, just remember you can always come back for reference, and you can also Google or ask ChatGPT and about the function, about how to write the code. So in one sentence, I describe the data table. It's just like anything you can do in Excel, you can do with the data table, just in a more elegant, efficient way. So firstly, let's see some basic features of the data table. We create a data table here, and we can see it's a columns and rows. Columns is some name, and each column has a name, has a variable. Just go here's this one. Now with some basic information, we can know the dimension is 6 by 10. That's 6 rows and 6 by 4. 6 rows and 4 columns. And we know, and it's just compare, they are consistent. The head, we will get the first 6 elements by default. So it's useful when we have a large data set and we want to have a brief look at it. We can just use the head function until it's just the last 6 column, and column names. And again, the structure and some statistical summary for the column. And we will give a example data set here, and to explore the data manipulation. The first one, we need to read the data set, and we can see it's flight information. It's in year, month, and day, and arrive time and carrier origin. Some are used, some data, some columns are in integers, and some columns are just a category, just a strings. So here's the overview of the flights dataset. We can summarize it for all the information. So the general form here is we have three arguments in the bracket here. The first one is subset rows using I and manipulate columns with G and grouped by bi. So here's a overview, and we will go some examples here. For instance, firstly, we want to extract some rows, which is remember, the first argument is for rows. Which rows? The third to four, and we extract two rows here. And a magic number is dot n. So we check n row dt is the whole length of it. So it's just extracts the last row. And if we use dt, and they are similar. So the dot n will just give us the last row. And if we want to do some conditional selection, we use a double equation, and we can give an additional condition, just use an and. Yeah, so here's some logic conditions. So we can explore the rows, the codes by ourselves. Next, after the selection, we can do the order things with a distance. In this way, we see the distance the rows will be ordered by distance from small to large. And we want to reverse the order. We just add a minus sign before the distance. And we see they're reversed. And next we will play with the columns. If we want to extract some columns, we just arrange. And you see why here there before we just escaped the row argument and we just leave it empty and go to the second argument here with the origin. But here is we got the values. If we add a dot before it, it's good. It will return us still in the data table. And same as if we want to do with it, these two methods, they are similar. They will return the data table instead of just the values. And again. And here is the exercise here. What's the advantage using C origin, using this method instead of the dot method? So I think we will just go through it and you can think about it. And the following examples will give you some ideas. The first one we can try use a C method. And here you see we have double dot. And we have double dot. We can play with it. If we only one dot, it will return an arrow with no, and that means must double dot here. And it will return a data table with two columns. And so it's just with a C method, it's just more dynamic. And again, we just move to the next step. In this step, we combine them together. We extract both the rows and columns. So we give both argument for the first argument and for the second argument. In this way, we extract both rows and columns. And next step, we do some computation on columns. The first one, we want to calculate, this example, we can compute the mean air time and return one value. And we want to know the unique origin. We want to give some tab. And unique origin have 3, although we have over 20,000 rows, but origin only comes 3. And with unique n, it will 1, 2, 3 give us a number of unique values. So furthermore, we can do some mean calculation, and we can quantify the origin from 1, like JFK, and calculate all the flights from JFK, the mean air time. And the last group is we can do by. We have seen the I, J, and lastly is by. We can calculate the number dot n, we just return the number for each subgroup. And by, we subdivide our data set by their origin. Remember, we have 3 origin, and dot n here is like the number of flights from each origin. So you see, you can imagine if you want to do so in Excel, that will take more time. So that's very elegant with data table. And here it's more fancier. We can just do 2 group by. So in this way, we have 2 origin. We have 3 origin, and for the destination, we have 71. That will give us origin times destination. And for each subgroup, we also return a number of it. Again, I will leave you with the exercise here. And it's very similar here. You can try by yourself. The number of unique values of a test airports by each month. That means we just change this one to months. And we can change their sequence. In this way, we can finish the task. So it's very elegant and intuitive. So here's a full command. We have the I, the row number. We select the row number with the month is 1, and we calculate the mean air temperature by this one, and we subdivide there by a region. So it's a full demand. And that's one. If the next one is if we want to drop some columns in place, we want to delete some columns, and we can use this one. We just the columns, we assign them as now. And you see here we still have year and day, and now we don't have the year and day, so we delete the first one. And if we want to change the column names, it's a little very tedious, but you can just copy and paste when you need it. We set names, we give the old names and give the new names, and skip absent. It's true. And this one is can avoid errors when we run it twice, because if we delete it already, and if we run this one again, the program cannot find the column names. So we can see original is dest and airtime, and now it's destination and flight time. Yeah. Next step, after deleting, knowing how to delete the columns, we start to add some new column. The first one we calculate the speed. Again, it's a column, so it's a second argument here. And we use the speed and distance divided by airtime. So it's just the row column name divided by another column name. And someone is the season. It's a F case here. We want to give a season, like give some months as winter, and give some months as the spring and as summer. We see what we can do here. We can check. For instance, the season here is just corresponds to the month number. For all month number, we give 12 for this month number from 12 to 2. And it's also very powerful, and it will give a conditional new column. And last step is if we finish our modification, we want to save, we just use the F write. And now, if you check your output, you will have a flight output CSV here. Yeah, it's very large, so don't open it. I'm sorry. Oh, yeah, we're back. So that's a basic introduction to the data table. And is fine with everyone, we can go to the next one, the geospatial data analysis. So with the geospatial data, what is geospatial? That's just like the coordinates is the coordinates is the geospatial. That means the location, and with some variable at each location. And we have two objects. The first one is vector file and it's raster file. So this one is a raster one. What is a raster one? For instance, if you want to represent the global temperature, then and how will you do? You cannot, because global is a continuous surface and we cannot do a continuous data set. So we just subdivide the global as each grid and we assign each grid a value. So just a raster data file here. The whole surface or the spatial is subdivided into many grids. And for each grid, we will assign a value to it. So just for instance, here is a topography. This one we just assign each grid with different like for instance, here is a river or the mountain, just give different information. And for in comparison, and we know here is a vector. And vector, how to plot this figure? That means the information for it is some it will be a sequential of points. We use the points to plot the curve here, and that can return us some information. So basically, with the geospatial data, like for some numerical data, we usually use the raster data. And the vector data file here is mostly used for plots the boundary and plots the continent boundary of many like boundary information. So here we give some example. We use the SF feature, and it's for the vector data. And we read some data. This one is you can imagine, you can think it's a raster data for DT site. It's a data USGS data site. USGS is a river it's a site with many riverine chemistry measurement, and we can do it like longitude and latitude. For each longitude and latitude, you can think of it like a grid in the previous figure. And we plot, we can have a result, we can have a feeling of it. You see, it's just like it's just like in the distribution just mimics the US continent. Next one, we convert to some geospatial data. With geospatial data, we give its coordinates, and CRS is a coordinate system. And we plot it again. And now you see, compared to the previous one, we have the latitude information and longitude information with the unit, and it's all the ratio is more appropriate to the real ratio. So here is like the raster data. And next step, we play with the vector data. And the first one gives a continental boundary. The second one gives us a distribution of US lakes. So we just play, you can just see the results. And with the current one, we plot the global distribution of lakes and our data points. Next one, we don't need to the global view, and we just need the US view. And here is our final result. We have the US boundaries, and it's plotted from the vector data set, and we have the data points is plotted with the raster data set. So all this you see is over 20,000. Yeah, it's over 20,000 data points, and it's a data set that Xiing's research relies on, and it's a lot of work. And for the time because we have limited time, and for this week for this workshop, we will focus on the data sets from the Texas. But if you are interested, and you can reach out to Xiing, and you can have more discussion for the future. So that's for the first basic one. And For next one, we can go through the physical model, and after that we can have a short break. So in this section, we will introduce a classical physics-based model, weathering model, and commonly it's also called the Western law. And just the necessary code to how to run this model. And here are three important references, very classical. So if you are interested how they derive the full form of the equation, you can refer to this reference. And you see, if you scroll down, you can see not many, just some equations here. I know it's a little scary to see some equations, but the core point here is not, we don't derive the equation one step by one step. We just give example like how to calculate the weathering flux just with this physical equation. So a basic idea is start from here. It's a yes. You see, you can imagine if we start from the weathering. So weathering model in the real world is very complex. The first one, we need an abstract framework to describe this question. And here in this figure, we see bedrock. It's just the continental crust or something bedrock. It's not weathered because it's not intact with the CO2 and atmosphere. And we have some regolith. You see, regolith is a layer of loose and fragmented material that covers the bedrock. We just assume the weathering mainly take place in this region. And we have some flux, like MC is a weatherable materials moving from the bedrock to the regolith, and ME is a mass of weatherable materials leaving this column due to the physical erosion. So, and we also have some weathering. It's a chemical weathering flux. So the weathering, the W here is something we care about. So the basic idea here is we assume it's a steady state. That means that the total mass in this column doesn't change with time. And due to the conservation of mass balance, and we see the mass here enter the system equals to the mass leave the system, and the mass enter the system is MC here, and the mass leaving the system is ME, is due to the physical erosion, and the weathering is a weathering flux. So basically we have the equation, the W is just equals to the MC minus ME. It's and divided by the delta T. So where the MC is here is also very intuitive. It's just a weathering at advanced rate. It's just the total materials entering the column and a fraction of weatherable, the fraction of weatherable materials. We just multiply them together. We can calculate the MC. And starting from this very basic form, and we see each term here, the dependence is on erosion rate. It's just like how much materials at a specific time can move from the bedrock to our column, and also temperature. And temperature can control the reaction rate and also the runoff, rock type, many things. And here, after making several assumptions and many calculations, with the previous studies, they derive a full term of the equation. It's a very long one. And we know we can divide the parameters in this equation into two categories. The first one is Q, the runoff, some environmental variable we can measure, and weathering advance rate and temperature. And these are the input for the model. And for other coefficients like these 6 coefficients, they need to be constrained from the data. So we come back here. The one question to employ this equation is, firstly, we don't have a catchment scale erosion data for the Texas region. one solution is we can calculate the erosion by the equation shown here. And also they are dependent on the relief, temperature, and discharge. We use this model, but we need to note that this equation, they are derived from different scenarios. And so it will also introduce considerable amount of uncertainty when applied to our study. So we just think we focus relatively small regions, so we will just assume a uniform constant erosion rate for the model. So we further simplify our approach. And for the next one is some parameters, like these 6 parameters are loosely constrained and they have a large uncertainty range. And because our idea here is just give you a intuitive understanding. So we just use a data set, a combination of data sets derived by West in his study, in his very classical study. So that means we assume these are constant. And after that, we come back to the equation. We have the values for each term and for each variable. And we only need to input the runoff and temperature, and we can calculate the weathering flux. So now we have the model, we can develop model. The input is the temperature and the runoff, and the model is a physical equations, and it can return the weathering rates in units of kilogram silicate cations per year and per area. So here is the model, here's a model that's realize the function here. So the most important thing for a physical model, I have several tips. The first one is always track the unit. And second one is to try your best to understand each term. So I will leave this to you if you're interested, you can explore it by yourself. And basically it's just realize the equation we shown before. And we apply to our research area, and we read a data file called influx, and this data file includes all the information from the Texas region. And we calculate. You see here, we have used the commands from the first R basics, and we create a new column and to convert the data units. So the first one is convert the units, and now we can calculate. Here is a new column, weathering rate, and we calculate, it's a function we read before, and the input is the runoff and temperature. And we load some plotting figures, and we can plot them. The weathering rate is ton materials per kilo square meters and per year. And this one is the runoff, and this one is the temperature. So it's again, you can see the whole workflow for the physical models. And we have some very simple interpretation from the results we have. The first one, we see the runoff and the weathering rate, they are very similar to each other. So we calculate the correlation coefficient. It's almost a 1, so they are highly correlated. That's not surprising, and because we see the temperature is in a relative short range, and we only have 2 input values. So runoff should be the controlling or dominant factors here. And it also aligns with our intuition. So since we know Texas is very hot and dry, and when the water availability should be the dominant factor. When there is water, the weathering can continue. When there is no water and no weathering. So you see, from the physical model, we know it's physics-based. It's very straightforward interpretation. But on the other hand, as we can imagine, are many other factors that can control the weathering flux here other than the runoff and temperature. But these other controlling factors are not fully represented in the model. So that means our model is less accurate, and it cannot capture the complexity of the weathering process. And that's a give you some foundation before the machine learning part.
So here's come to the last part, and in my part, I'm going to tackle with some real world data by using the machine learning. And is like we just mentioned that rock weathering is an important process which can impact the carbon cycle. But instead of using the traditional method here, we are going to use the data science or machine learning methods to deal with that. And I'm going to walk you through one thing that I love about Jupyter Lab is like you can see all the sections here and it's pretty clear. And I'm going to walk you through all the data, the river chemistry data and the environmental variables data that we're going to use. And we take a look at the data and how to combine them together. And finally is the machine learning part. So let's begin with this. The goal of this section is to use environmental data and machine learning to predict rock weathering flux, which I think is pretty clear. And we just mentioned that in Shihan's part, he mentioned how to calculate rock weathering flux. It is calculated by the concentration of bicarbonate times runoff, and runoff is calculated by discharge over area, which you can both measure from USGS. And here we have the data. We read the data of Texas, including the flux data here. And we have this is how data looks like. We have different site numbers, or set names. They are all from USGS in Texas. And we have the information of geographic, like longitude, latitude, and also the time, like the month, year. And we just mentioned the discharge, the area, and the runoff calculated from that. And we also have the alkalinity, which in the river system, the bicarbonate is the domain species of alkalinity. And here I calculated alkalinity from silicate weathering and carbonate weathering, use an inverse model, which we're not going to cover here today, but feel free to ask if you're interested in. And with this, for example, the alkalinity from silicate weathering times runoff, we can have the flux of silicate weathering. So we have the silicate weathering flux here and carbonate weathering flux with the unit around them. And we can also see the spatial distribution, which is similar as what Shihan mentioned in the first section. And we read the US data and the US shapefile. And here I want to mention that this small function here, the SFUS S2, when you met some problem with our shapefile, so this function can solve 80% of the problems. Yeah, so just keep that in mind. And if you ask ChatGPT about your error, it can like fail troubleshooting. But with this, it works pretty well. And we also read the watershed shape file and also convert that into some simple features. So here is the river chemistry station in the US, and the red dots are the station that we observed, and the blue shaded colors represent the watersheds. And we can also zoom into the Texas here by using the STB box here, which is using a bounding box. And here is the map. And you can see that the watershed is actually overlap with each other by telling the transparency of that. And another thing that I want to say is the watersheds are actually extending outside the Texas. So the data point that you collected is within Texas, but the watersheds are actually more than just in Texas. Does that make sense? And we can also take a look at the temporal distributions. And if you want to know that how the frequency of the month that you collected and the year you collected, you can just use a simple histogram here. And you can see that the months are relatively evenly distributed, but the year is frequently collected in around 1980s. And if you want to combine the year and the month, you can also use a heat map like this. On the x-axis, you have the month, and on y-axis, you have the year, and the color represents the sample counts. And you can see that also the frequent samples around the 1980s. So after taking a look at the data, we can do some pre-processings. And the goal of pre-processing is for each one station, we want a data point. And usually you can see an example like this. You have the set number, you have the year, and the different month. One way is technically you can average all the data and to get one data point for one site. But there's some problem with that. Like not all the data are as perfect as in 2012, which you have all the month data. Like there are some data like in 2005, you only have the October in fall, which definitely cannot represent the whole year. So to tackle this problem, one way is we just average them step by step. And we first start with the season mean, like you have different months. Here's an example for the first USGS dataset. You only have the month of March, June, and and January, these 3 months. So we need to give the tag of the different seasons for them, like from December to February is winter, and the following seasons are similar. So you have a new column here, which is named the season. And after that, we select only those with the 4 seasons that represent that you might have the whole year data. And only season is equal to 4, which means you have 4 seasons, and we select those data and average that over a year. And you can see that you don't have the month data here anymore because month is useless and you only have the year. And the next step is to the interannual mean, which you want the long-term average or the climatology data, which you just average all through the years, like the different years. And you can see here that all the time data or time informations are gone. This is because our final goal is to, for each data set with one flux value. And by checking the number of rows of the original data and the data that we average for the climatology, we can see that we cut that from 23,000 to 220. And you can also check the map here, and you see in the data points represented by the red dots here are less dense than before. So the next step, we are going to take a look at the environmental variable data. And as we mentioned before, rock weathering is a very complex process, which is controlled by so many different factors. So I think that from my point of view, the machine learning is the best way to study this complex process. So we can check the data first, take the temperature for an example. It is average from 1980 to 2010. And the TIF is another common format for the geographic data. And it is usually represent the raster. Remember that we mentioned the difference between raster and vector before. So after reading the raster inside, we can check the resolution of that and the dimension, also the longitude and the latitude. And here's another thing that I want to mention, like the longitude and latitude information here is pretty weird, which is not what we saw on Google Map. So this is because the one term named Coordinate Reference System, or short for CRS, the CRS for the raster here, it is the EPSG is equal to 5070, which means it is calculated by the meters, the unit is meter instead of degree. So to convert that, fortunately, we can use a symbol project function here to convert that to 4326, which usually we need to memorize these different codes. And for this code, it represents the longitude and latitude, which is in the unit of degree. And also you can check that and see the X for longitude and Y for latitude is what we are familiar with now, is like the normal longitude and latitude. And technically you can use the R code to show the map of the spatial distribution, but you see that there's a warning here because the raster or the TIF data usually has a lot of information inside, and running that might cause the kernel to crash, and it would take a lot of memories and very time consuming. So I wouldn't run that, but if you want, you could do that. And apologize that if you don't have this figure here because I feel we forgot to update that. So the result shows like this. It only takes about 30 seconds, but it takes more time to plot this figure here. And to solve this problem, I would recommend using the QGIS instead of like plot that in R. So the QGIS is an app for visualization, which is pretty fast, and you can easily drag all the TIF data inside and see the spatial distribution like this. In the next step, we already seen the chemistry data, and we saw the environmental variables. So we want to combine them together. And there are two different ways to combine them together. One is by pixel and another is by watershed. And we're going to go through them one by one. So here are some basic concepts. The stream is just the water shown in the blue color here, which can change with the time, like depending on whether the year is floody or is dry. And we also have the I don't know what color is it. This color, the watershed, which it doesn't change with time. It's just the land area, which you can also measure or get the data from USGS. So the goal here is to combine the station, which in the black here, with the background, which is the raster of the temperature. And the first method is by pixel. So the by pixel is relatively easy to understand. You can imagine that you're playing a game named Find Your Nearest Neighbor. And we can easily use a function called st nearest feature here. And with this function, the water chemistry, they just check in and find the nearest temperature body here, and they combine them together. So why would we find the nearest instead of the exact combining them? This is because you can see in the cell 23 here, the longitude and the latitude, or the geographic information in temperature, actually doesn't match with that in river chemistry. So it means we cannot just combine them by longitude or latitude. We have to find the nearest one. So with this function, we can get the DT merged by pixel. Here you have the site information, the longitude, latitude for river chemistry instead of the temperature. And in the end, we have the flux values and the temperature. So this is the first way that we combine the flux and temperature together. And another way is to use the watershed. That means like considering the watershed is a giant mixing bowl and it collects everything from the upstream. And we use the exact extract here to combine the station with the watershed. And some advantages of using this function, the first one is this function is based on C++, which means it is very fast and memory efficient. And another advantage is like, for example, here we have this watershed. So why did we select these from the intersections and excluded these two? This is because we know that most of this pixel or this polygon is within the watershed. So, well, a good thing about exact extract function is it can do this thing automatically. It can weighted the extraction, like use the area weighted mean, which is a built-in function here to extract that automatically, so we don't have to do that manually. And another good thing is, well, it is very flexible. Here we are just calculating the mean value, but you can also calculate the sum value or the median value here. And this is the result of our merged by watershed. We have the temperature from watershed here, and the rest of them are similar as before. And we can also compare these two methods, and the names of them are mostly the same except for the temperature that by pixel or watershed. So to illustrate that, we can either use a box plot or the density plot. So the box plots are telling you that which is higher and which is lower in the distribution of that or the frequency of that by the density. So we can see that the watershed temperature is not much lower. It's a little bit lower than that calculated from the pixel. We can also see the spatial distribution and noted that there are some different trends, like these data are being smaller than the environmental than the environments. So here comes the question, which one is better? And the answer is watershed. One way is to consider it as from the perspective of temperature. Imagine that in the summer and you bought ice cream, and if you just measure the temperature on the ice cream, you can feel that it is pretty cool, and you see that the temperature around that single data point is pretty low, but it cannot represent the whole summer environment here. So that's how you consider from from the temperature. And another way is to consider it as from the perspective of weathering flux, and also consider this example that your ice cream is melting and you're very sad. You want to measure that how fast it is melting. Instead of like measure one of the drip from your ice cream, you want to collect all the drips around the ice cream. So this is why we use watershed instead of like a single point. And I hope that's clear. So the next step, we are going to take a look at the real data. And as I mentioned before, the silicated weathering or the rock weathering is a very complex process. And the temperature that we just took, for example, is only one of the impact factors, but there are so many different factors. And following the same logic, I have already combined all the data sets for you, and we have these different variables, and we have the on the last column we have the flux values. So this is combining the river chemistry with the environmental variables. And we can also check that if there is any missing data, and it shows that there's no missing data, which is perfect. and to check the minimum and the maximum value of the flux. And we can see that we use a logarithm for transformation here. It is because the flux values are varying from across a very large scale. So to avoid the skewness, we usually use a logarithm transform for the flux value. And here we take the silicate weathering for an example, which is considered as the target here, and we use the log scale here. And we also have the predictors, including all the variables. So we can scatter that, and this is the most intuitive way to see that how the different variables impact the silicate weathering flux. And we can see that for the precipitation, there is a significant positive relationship, and for land elevation, there is a negative relationship. And another way is to use the correlation coefficient. And here we use the Spearman correlation coefficient. It is because, so there are two different ways. One is Spearman and another is Pearson's. And here we use the Spearman because it can capture some nonlinear relationship. So it really doesn't matter if you use the logarithm scale or not. And after calculating the correlation, we sort it by the descending order of absolute correlation here. And here is the figure. And it can easily tell you that which is the most important or which one has the highest correlation coefficient. And the shading color here represent the significant. Any questions so far? Okay, and then let's move on to the machine learning part, which is pretty exciting. So this is the comparison between the traditional method and the machine learning. So for the traditional method, we usually have the input and we give them the rules of the programming, and we have the output by following the instructions of the rules that we gave. But for the machine learning, we feed the machine learning algorithm both the input and the output. And the machine learning algorithm will calculate a program for you. And you can use this program and to gain some new inputs from your gain some new output from your new inputs. And here I'm going to introduce two methods of machine learning algorithm. And raise your hand if you have ever heard of random forest. Yeah. And what about the gradient boosting? Okay, perfect. So I'm going to tell a little bit about the random forest and the difference between random forest and gradient boosting. So for the random forest, we usually have different trees and we calculate them together. And this is more the strategy of random forest is what we call the majority wins. So we make the decisions together, like by individual, and then we have the statistic of which one is the majority, and we consider it as the final result. This is for the classification. And for the regression, we just simply take the average of all the results. And for the gradient boosting, you can consider it as a different way, like there is another person sitting in the corner and learning all the mistakes by his friends in the group discussing together. And so it is like doing the decision trees step by step or in sequential. So this is the difference between the gradient boosting and the random forest. And here is specific comparison between these two methods. And so both of them are actually very efficient, but random forest has tend to overfit data. And from my understanding, the XG boost is actually more accurate than the random forest one. But it does require some careful tuning. And here is an important concept named decision tree. So we start from a root node, which is the only one, and this is an example of the temperature prediction. And we have some decision nodes by telling that is that true or false. And you can see that how many decision nodes are here. It is 6, right? And after this decision nodes, the final decision nodes, you can consider it as the final one without any branches after that. It is called leaves. And another concept that I didn't put here is called tree depth. And tree depth is more like when you're playing the game 20 questions and I ask you, is this an animal? And you say yes. So this is the tree depth is equal to 1. And if I continue asking that, does it fly? They say no. And this is, you have 2 information. This is the tree depth of 2. And if you continue asking that, does it have 4 legs? And I say yes. So this is the tree depth of 3. And based on this, you can probably have your guess or have the leaf that it is a dog. So it is the concept of different terms here. So we need those preparations for the machine learning. We extract all the subsets of the predictions and the target variable. And usually we put the target variable on the last column, like here. Here we're predicting the logarithm of the flux value. And this is a good way to illustrate the correlation between your predictors. Like you can see that there are some variables that are closely related, like the precipitation here and the runoff here. So the higher precipitation will result in a higher runoff, which makes sense. And so for now, we haven't had any machine learning yet, just the statistic method. And usually we split the data into the training and the test data by 80% and the 20%, or you can also do the 70% or 25%, just depend on what you're focusing on and your specific question. And this is, yeah. And the first method is random forest, we just mentioned. So the basic of random forest is actually pretty clear. In the first step, we train the model, use the ranger here, and we have the predictables here and the target here. So it is an easy way to use the ranger. And here I want you to notice that the number of trees here is actually 500, which is specific value, which means come back to this figure, we have different like 1,500 trees here. And after training the model, we can see that how the model performs on the training data by calculating the R-squared, and we can use this this function, this library, and with the function of R2 score to calculate that automatically instead of like using the 1 minus something like that. And we can see the training, the R score on the training data set is about 0.92, which is actually pretty high because your data, your model is trained based on your data here. So it makes sense. And we can also plot the scatter of the training data with the predicted value and the actual value here. We can see a perfect positive line here. And then we apply this model to our testing data, which is the 20% of the data that we have never put into the training model. And the R score for the test data is about 0.76. And also we have the scatter plot here. So that is basically all the flow of the machine learning for the random forest, which is actually pretty easy. You just train your model, you predict with your training data, and you predict with your testing data. But there is another way that using the k-fold cross validation, which we just mentioned before, that the n tree or the number of the trees is a fixed number, the 500 if you remember. But here we are using the k-fold cross validation, which we can split the data into different data sets, and we find which we are changing the number of the trees and to find which is the best way to change this tree number. And it is also can be realized by using a package named MLR. So yeah. So before performing the training, we need to set up the task, and we need to set up some learner, which you just follow the some fixed format like this. And then you can do the hyperparameter tuning using the grid searching with cross validation. This so 500 is what the fixed value before, and we also included that inside. And we can also change that around these 500 values. So here I choose 300 to 1100, but you can vary that according to your specific research. And also we can change the node size, which is remember the node size? Yeah, like these different decision nodes, and each one is one node size. Node, yeah. So after the switching, we can also set up the number of the folds. The number of the folds is actually, so for this one, this example here, the k is equal to 5, but we can make that as 10 to get more data sets splitted. It's like you are cutting a cake into different different slices, and you taste each of them, and you say that what is a ingredient of this one and what is the ingredient of another one, and pick up the best ingredient. So here we choose the k-fold is equal to 10, and this would take some time if you choose more tree numbers and more nodes sizes, but I have already run that before. So it took me about half a minute to do that. And here is our result. We found that the best number of tree is 900 and the best node number is 4. So we can use this new number of trees and the node size to apply to our training model. And the rest of them are actually following the same structure of the basic random forest machine learning. And we also have the, I put that here, recall that for the basic training, we have just the two rows for that. One is your formula, which is the target, and another is the data or the training data here. And for the new the new one, we can also add these two, the number of trees and the number of nodes here, which can help us to optimize the result. And so this is the performance on the training data and also the performance on the test data. So, but for this one, because remember that our data set are only about 200 data points, which is actually a very small size. So if you apply this one to a larger data set, let's say around 2,000 or to 20,000, and then the result should have a significant better performance. Any questions so far? Okay, so the second method is using XGBoost, and we also splitted that with the same method, the 80% and the 20% before. And when we so one step to using the XGBoost is you need to convert that into some specific format here. And after the preparation, we can set some parameters. The first one is the learning rate. So you can consider the learning rate as remember that we are doing that tree by tree, and so the different learning rate is if you do 3 trees for a specific time, or you do 30 trees for a specific time. So that is the difference of the learning rate. And the max depth we just mentioned is how many questions that I gave to you, like when you're playing the game 20 questions. And we have the subsample of the training data, which you can choose like 50% of your training data to do the training model. So the training is like this, and you can set an early stop rounding to avoid the overfitting, which I found that it is very important. If you change the number, the result will change, which you can try by yourself. And this is how the model performs on the training data set. And you find that for the R-square for the training data set, remember that for the random forest is about 0.92, but for this one is 0.98. So it's actually a significant increase for the enhancement from my point of view. And this is the symbol scatter for that again. And we can also predict that on the testing data. And for the testing data, the R-square is 0.79, which also has a better performance than the random forest one. So the last part, we can use the XGBoost to see the feature contributions. So to simplify that, the feature contributions is to see that which one is the most important for your model, for training the model. And they have, for the XGBoost function, they have the default one that you can use, which is the XGBoost importance here. But you can also calculate by hand, which using this one, the importance matrix, and you can draw the figure with a better, I don't know, like settings here. So here is some take-home messages. Oh, I forgot that. So for the combining by the watershed, there is something that I want to say. So I might be the only person who's studying on the watershed here, but if you're learning something else like the environment, the soil, and the sediments, it is important to know that whether the influence of a specific process is local or the remote. So like the example here, the temperature's influence on the water chemistry or the rock weathering, it is definitely not on a specific pixel. So we consider it as the average of the watershed. So it is important to keep in mind what you are learning about, and is that a local influence or it is an accumulation effect. And for 3 take-home messages for you, the first one is we compared the traditional method based on the physical model and the machine learning or the data science method. And for the machine learning algorithm, we compared 2 different methods. One is random forest and another is XGBoost. For the random forest, it usually used the parallel trees, and the XGBoost used the sequential trees. And we got the conclusion that XGBoost is has a higher accuracy than random forest. And the last one is some factors of the scientific conclusion, the factors impacting silicate weathering. And we found that runoff is the key factor, which is confirmed by both the traditional method and our machine learning here. And also, another thing is the machine learning captures the importance of some other variables like the elevation, which is the contributes the most, and also the population. So this is what the traditional method cannot do. And that's it. Thank you all.
So something it's a summary by myself. It's like some intuitive feeling about the physical model and the machine learning. So basically, they have some similarities. They are similar, and machine learning, they are not a black box, and they both are mathematical equations. So the essence for any model is mathematical equation. But for physical models, you describe different processes, the form of equations will vary. But for machine learning models, the form or the whole framework often can be applied to different problems. And lastly, second, you see in the second part, we need to tune some parameters. We need to use data to tune some parameters. And for physical models, but for machine learning models, there are also some parameters to tune. You need to tune the parameters and it will return you some results. You need to tune your model. But usually physical model, when you run a physical model, you don't have the parameters have physical meaning. But for machine learning parameters often don't. For example, the number of trees, the number of nodes, there's no physical meaning. And both need data to calibrate these parameters. Like for machine learning, you really require a much larger data set. So, and the last one is they are just similar, like they have their pros and cons. And one emerging field or one emerging methodologies called like physics, they just fuse the physical model and machine learning. It's something like the physics informed neural network, and also pretty fantastic. So that's all for the materials today. And since we have a lot of just before that, let me share. The ASIC system is supported by the NSF, and also we thank to the staff and students from the HPRC Research Computer Center, and we appreciate this. It's also supported by the TAMIT's Data Science Student Ambassador Scholarship Program. And for the last one, I want to give the ambassadorship scholar program. They will start the new year recreation, and if you have interest, you can apply for it. You can just search it, and you can see it. And you can read the instructions, and you have interest, you can apply for it. It's also an awesome opportunity. I think that's all for today's workshop. And here is a short course survey. If you have time, you can scan the code and you can fill up it. So we order pizza for everyone and probably needs 10 or 20 minutes. It's a little faster than our expectation, but since I think the code here is very dense, so we will give you enough time. You can play with code or explore the code, and we'll stay here. If you have any questions, you can ask and discuss. And if you want, and we can wait for the pizza, and we can take some pizza. And if you want to leave, you can feel free to leave now. And I think that's all for today's workshop. And thanks you all for coming. Yeah, really appreciate it. Yeah.